All right, let's talk about vectors. Some physical quantities have not only a magnitude but also a direction. Think about you walk from here to the grocery store. That has both a distance to the grocery store and also you had to go north, south, or whichever way in a particular direction to get to the grocery store. So your displacement vector would say where you went from here to the store. Quantities that have only a magnitude we call scalars. So a scalar has only a size, and vectors have both a size and a direction. Let's talk about how we add, subtract, and multiply vectors. Okay? A vector is a direction from one point to another. Let's call this vector A, and I indicate that it's a vector by drawing the arrow over the top of it. So this is vector A. It says to go this far from that point up in that direction. Okay? That's the same vector whether I start it here or not. It's just an instruction from wherever you start to go this distance in that direction. Okay? Let me draw another vector, B, in a different direction and with a different length. Okay? And now let's talk about how these vectors, how to combine these vectors. So suppose I ask you to add A plus B. Okay, the operation is A plus B. What does that mean? That means I follow instruction A and then I follow instruction B. Okay, and the sum of those two vectors is the net instruction. So I follow instruction A from here to here, and then I have to follow instruction B. So I have to put the tail of the B vector at the head of the A vector. So I've reproduced the B vector here. Okay. I put the tail there and I do this instruction. And the answer to A plus B is to go from here to here. In other words, applying the A vector then the B vector gets me here. Now, the addition of vectors is commutative. I can also write this quantity, B plus A, is exactly the same quantity. It just means I do instruction B first and then I do instruction A. So how would that look? Here is instruction B. So let's say I do that. Let me start at the same spot. So I'm going to move this vector B right here. So I do that instruction first. I go here to here, and now I do instruction A. I go from here up here. And you can see that adding B plus A is identical to adding A plus B. That's true for any two vectors in any directions. All right, everybody clear on addition of vectors? We'll practice in a bit. Now I want to talk about subtraction of vectors. My vector A. Remember that my vector B looks like this. If I want to do, let's say, A minus B, that is basically A plus the opposite of B. Okay? So if this is B, then minus B just points in the other direction. So the subtraction A minus B is the same as adding the opposite of B, negative B. And I know how to add. I do the first instruction, then the second instruction. Okay, so this is A, and now I do negative B. And then my answer is this vector. This is A minus B. Here you can clearly see A minus B is not going to be the same as B minus A. Okay, because in the one case I'm flipping B, and in the other case I'm flipping A. So I'll get a very different answer, but let me just show you what that looks like. So if I have B, B is this way, and now I'm going to add negative A. That has to be like this. This is minus A. And you see that the sum is B minus A. And B minus A is minus A minus B. Do you see that? A minus B is the opposite of B minus A. They're exactly the same length, but they point in opposite directions. So now let's talk about multiplication of vectors. First, I can multiply a vector times a scalar. Remember, a scalar is just a number without a direction. So if I have a vector A, and I multiply it by 3, it just becomes 3 times longer. Same direction, but 3 times longer. So 3A would be this vector. Okay? If I multiply by a negative number, the direction changes to the opposite direction. All right, that was the easy multiplication. Now let's do a slightly more complicated multiplication. How do I multiply two vectors? So I want to have vector A times vector B. And it turns out there are two versions of this product. One is called a dot product, and one is called a cross product. We're going to learn both, but let's start with the dot product. The dot product of two vectors is defined as a number. It's not a vector. The dot product is not a vector, it's a scalar. And it's equal to the magnitude of A times the magnitude of B times the cosine of the angle between them when you put them tail to tail. Here's my vector A. Vector B, let's say, is this. And I've drawn them tail to tail because the angle between them is defined as this angle when you put them tail to tail. It's the smaller of the two possible angles, the other one being this large angle. So A dot B is equal to A times B times cosine theta. That gives us a sense of what this dot product actually means. It is the projection of one of the vectors along the other vector. So for example, it's the projection of the length of B that is in the direction of A. Okay? So you can think of B as a part that's along the direction of A and a part that's perpendicular to the direction of A. This is like a component of B this way, and this is the component of B that way. Or another way of saying it is those two components, one in the direction of A and one perpendicular to it, add up to B. With me so far? So B cosine theta is the length here of, it's the part of B that is along A. You see that? Okay, let me say it again just to make sure this is clear. It's the projection of this vector B onto vector A is the length of B that is along A. And then there's a length that is not along A, and that disappears. Okay? It is also the projection of A along B. Let's look at that. So here's the vector A, And B is in this direction. So the projection of A along B is here and parallel. So the projection of A along B is the amount of A that is along B and then the amount that's perpendicular to B. For most of what we'll be doing, we'll be dealing with two-dimensional or three-dimensional problems. So we'll have let's talk about two-dimensional problems like in the space of your blackboard. There's a vertical direction and a horizontal direction, for example. Let's call the vertical direction Y direction and the horizontal direction the X direction. So axes, I'm suggesting axes like this, Y direction and X direction. Then any vector, any arbitrary vector A or B can be described as a combination of its X components and its Y components. Let's see how. Let's go back to vector A here. Let me make it a little more clear. This is vector A. What are its X and Y components? Let me get rid of vector B for the moment. We don't need it at the moment. Here's vector A. What are its X and Y components? So I ask, what is the amount of vector A that goes in the X direction and the amount that goes in the Y direction? And you can see how this component plus that component would add up to A, right? This much of a vector in the X direction and this much of a vector in the Y direction add up to vector A. So I can say that A is the sum of its X component, let's call that AX, and its Y component, AY. This is where it's convenient to introduce unit vectors. We commonly use the notation I with a little hat to mean a unit vector in the plus X direction. J is a unit vector in the plus Y direction. These two unit vectors allow me to write vector A as its length in the X direction, AX, times unit vector I, plus its length in the Y direction times unit vector J. I can describe any vector that's in a plane as a combination of two vectors in the orthogonal units of that plane. Let's bring this all together, the dot product and the unit vectors, and talk about the dot products of unit vectors. I remind you the dot product is the length of vector 1 times the length of vector 2 times the cosine of the angle between them, right? If I were going to draw the unit vectors here, in the X direction, I have a unit vector I, and in the Y direction, I have a unit vector J. What's the angle between I and J?
Theta.
Theta, right. What is the value of theta?
90 degrees.
90 degrees. Okay, what is the cosine of 90 degrees?
0.
0. So, now that I've prompted you, what is I dot J? 0. It's the length of I, which is 1, times the length of J, which is 1, times the cosine of 90 degrees. But that is 0. So these are called orthogonal vectors. No component of I is in the direction of J, and no component of J is in the direction of I. They are orthogonal or perpendicular. This gives us a way to do dot products mathematically, not just looking at the cosine. Suppose you have two vectors described in terms of I and J, but you don't know, a priori, you don't know the angle between the two vectors. So you couldn't easily use this formula to determine the dot product. There's a very easy way to do the dot product that doesn't involve knowing the angle, and that's to use the unit vectors. Suppose vector A is equal to an X component times the I vector, plus the Y length times the Y vector. And similarly, we have vector B, which has an X component, Bx, and a Y component, By. Whatever vector A or B I give you, you can always figure out what its X and Y components are, and I'll show you how to do that in a moment. And then when you have these two vectors, you can easily do the dot product. let me just do one or two more dot products to make sure you're with me. What is I dot I equal to? What's the angle between I and itself?
180 degrees.
It's basically, well, or zero, right? They're pointing the same way, so there's zero angle between the two vectors. They're the same direction. So this becomes 1 times cosine of 0 degrees, and cosine of 0 is 1. So this dot product is 1. And it's also j dot j is 1. So I dot I or j dot j are 1, and I dot j is 0. But now let's learn how to do the cross product. It's a little bit of algebra here coming, so you may want to do this on your pages at your desks. What is A dot B when I use this notation with AX, AY, BX, and BY? Well, it's AXI plus AYJ dot BXI plus BYJ. We can multiply out these terms. The dot product distributes just the way ordinary multiplication does. So I can take what's in the parentheses dotted to what's in this parentheses is simply AXI dot BXI plus AXI dot BYJ plus, now the second term, AYJ dot the first term here, BXI. And finally, AYJ dot BYJ. All right, so I've now just multiplied these two terms times these two terms to get 4 terms. Let me rearrange them slightly. So I have AX BX times I dot I plus AX BY I dot J plus AY BX J dot I plus AY BY J dot J. Okay, it looks a little complicated, but because we talked about how unit vectors interact, you immediately see 2 of these terms are 0 because j dot I and I dot j are 0. So these 2 terms go away. And you're left with the dot product being 2 terms that are scalars. What is I dot I?
1.
It's 1. So AX BX times I dot I is just AX BX. And this is just AY BY times j dot j, which is 1 also. So the net dot product is AX BX plus AY BY. These are 2 numbers multiplied, another 2 numbers multiplied, and you have the magnitude of the dot product. So if you start with a vector that is in IJ notation, you can very easily determine the dot product without ever knowing the angle between the 2 vectors. In fact, you can use this to find the angle because you can get the length of A, the length of B, and you know this, then you can determine the cosine of the angle. So you can actually use it to figure out what is the angle between 2 vectors. So let's do an example to show how this works. If you make an xy axis, we can define 2 vectors in terms of the unit vectors. And here we'll just deal with dimensionless lengths. So let's have an A vector, which is equal to 3i minus 2j. Okay, what does that mean? I go over 3 marks on the x-axis and down 2 on the y-axis. So I end up here. So here is my A vector. Okay? And let's have a b vector that is 1i plus 4j. So that would be 1 in the x direction and then up 4 ticks in the y direction. 1, 2, 3, 4. So that's my b vector. Okay? Let's start by doing a plus b. Okay? What is a plus b? Well, I take vector A, which is 3i minus 2j, and I add vector B, which is I plus 4j. Now I'm just going to rearrange terms to group like terms. So this becomes 3i dot I plus 3i dot 4j, which is 0, plus a negative 2j times 4j, which is minus 8, and then negative 2j times I is 0. So this becomes 3 minus 8, and that equals minus 5. Ready for the cross product? Okay.
Yes.
I should stop here and say, when I first took physics, oh gosh. When I first took physics, I thought physicists had made up the cross product just for like equal time with the dot product. Like the dot product is the scalar, so they made the cross product a vector. And the length of the cross product involves the sine of theta. So I really thought this was just like equal time for sine angles as for cosine angles. It turns out, of course, the reason we define these products, the dot product and the cross product, are that they're useful in physics laws. We're going to need them for what comes. That's why we're learning it now, is so that we're ready when we talk about dot products and cross products in talking about torque, for example, or force. Okay, so onward to the cross product. As we just learned, a dot product is one way of multiplying two vectors, and it's a way that results in a scalar answer, a number. The dot product of two vectors is not a vector. It's just a number. And I gave you a sense of the physical meaning of it, which is the dot product of two vectors is the projection of one vector along the other, or vice versa. Now we're going to talk about something more complicated, the cross product. It's a different way of multiplying vectors, and it's important for certain laws of physics, and that's why we're learning it. But it's very easy to do once you understand the IJ unit vector notation. So first I'll give you some definitions, and then I'll give you examples for how we do it. The cross product of two vectors, A cross B, is equal to a vector. Its length, the magnitude of A cross B, is the length of A times the length of B times the sine of the angle between them. I already showed you how to find the angle between two vectors. This product depends on the sine between the two vectors, not the cosine, and it has a direction. And the direction is given by the right-hand rule. What is that? First of all, how many of you are left-handed? Okay, 1. So the left hand is always start to use the left hand, but I'm afraid this is the unfair rule of the majority of right-handers. We use the right-hand rule. So now you're going to learn it. Take out your right hand. You put your fingers in the direction of the first vector, so vector A. So here is vector A, okay? Put your fingers in that direction, and you're going to curl them toward vector B through that angle theta. And your thumb is pointing in the direction of the resultant vector. So A cross B is perpendicular to both A and B. It goes in the direction your thumb is pointing, which is out of the board. Everybody got that? Okay. So let's write down that the direction comes from the right-hand rule. A cross B comes out of the board. So we draw out of the board sometimes as a little circle with a dot in it. That's supposed to represent an arrow coming out of the board. And if it's going into the board, I'll draw it down here because it's not this vector. We would draw a little X, like the back of an arrow, like the tail fins of an arrow, the arrow going that way. Okay? So cross products are inherently three-dimensional. If any two vectors define a plane, and the cross product is always perpendicular to that plane. So far, so good? Okay, in order to do 3 dimensions, we can't just use I and j anymore. We need a third vector that's in the z direction, because we need 3-dimensional space. So the traditional right-hand system defines an axis coming out of the board, the z-axis. You have a choice, right? It could come out of the board or go into the board, and this is a right-handed system where x cross y, or rather I cross j, is equal to the z direction. Everybody see that? This is my x vector. This is my y vector. So the z vector has to come out of the page in the right-hand system. And we call the unit vector in the z direction k. You probably could have guessed that. So I in the x direction, the unit vector in the y direction is j, and the unit vector in the z direction is k. So now we can, with a lot of algebra, easily show how to calculate A cross B. Remember, the answer is a vector, okay? And the reason is because A is going to consist of I and j components, B consists of I and j components, and I cross j gives you k. So the answer is going to be in the plus or minus k direction. Let's just review. I cross j. What is that? I cross j. So it has a magnitude of 1 times the sine of the angle between them. The angle between I and j is 90 degrees. The sine of 90 degrees is 1. So the magnitude of this vector is 1. What's its direction? Its direction is k. So I cross j is equal to k. Okay, let's do a little bit harder one. What is j cross k?
I.
Okay, put your fingers in the direction, right hand only, fingers in the direction of y. Curl them in the direction of k, which is coming out of the board. So you got to turn that way, right? Fingers, yeah, you got to be facing, you got to be facing that way. Your fingers got to be facing that way. Yep, there you go. Curl. Then this is the direction of the product, the cross product, which is what? I. So j cross k is equal to I. Everybody got that? You want that again? It's y cross k, which is coming out of the board, is equal to I. J cross k is equal to I. Okay? All right, how about k cross I? Okay, k is out of the board, so you have to go that way. And then you want to cross into I, which is that way. So I got to go like this. And I've got j. Okay. What about I cross k? Just flip it around. I've changed the order now. I cross k. The order matters. So I is this way, okay? And k is out of the board. So I come up with minus j. See that? If you flip the order, then the sign changes. So right away we know, for example, A cross B is equal to minus B cross A. If you flip the order, you change a sign. Last thing we're going to do is show how we do a cross product in the presence of components. If we know the component, the x, y, and z components of two vectors, how can we do a cross product? You can get the cross product if you know the lengths and the angle between it, and you use the right-hand rule. So that's one way to get the cross product. It's got a magnitude, AB, sine theta, and a direction given by the right-hand rule. But if you instead have two vectors that have ijk notation, you don't necessarily know the angle between them, and you don't necessarily know which way they're pointing, you can still get an answer, a correct answer, by using the unit vectors. So let me show you how we do that. And here, I'm not going to show like draw an example. I'm just going to use algebraic notation. So let a vector A equal an x component ax times the I vector plus a y component ay times the j vector. And similarly, B will be bxi plus byj. Okay, so this is completely general. The by could be a number, it could be a miles per hour if we're talking about a velocity problem, it could be anything. So we're doing the most general case. So A cross B, oh, it's not the most general case because I didn't give you the z terms. Shall I give you the z terms? That will make 9 terms. It'll be a big mess, but let's do it. We're not scared of algebra, correct? So let's have them all have a z term as well. azk and bzk. So that's the most general description of a vector in 3 dimensions, broken down into its components. So A cross B is this whole thing cross this whole thing. Okay? That means this term cross this term plus this term cross that term plus this term cross this term. Okay? Then the second term cross the first, the second and the third term cross all of them. So you have 9 multiplications. Okay, so that looks like ax times bx times I cross I. That's the first term. The second term would be ax by times I cross j. And the third term will be ax bz times I cross k. Now I've got 6 more of these, all right? Okay, so we have ayj cross bxi. So that's ay bx j cross I. Then we have ayj cross byj. So we have ay by j cross j. And ayj cross bzk. So that's ay bz j cross k. Okay, whew, 6 down, 3 to go. 3 more. So now we do az cross each of these. Okay, so I have az bx k cross I plus az by k cross j plus az bz k cross k. Everybody see how I got from the multiplying the 2 vectors? Now I've just made them into individual cross products of unit vectors. Okay. Okay, 3 of these terms are 0. Which ones? The one with the same unit vector. So I cross I, j cross j, and k cross k are all unit vectors in the same direction, meaning the angle between them is 0, meaning the sine of the angle is 0. So I cross I is 0, j cross j is 0, and k cross k is 0. So I get rid of 3 terms, and I'm left with 6 terms. Okay. We already learned what I cross j is. Remember that I cross j is k. So here's an I cross j term. And here's a j cross I term. Now remember, I told you when you switch the order, so if I cross j is k, then j cross I must be minus k, because switching the order changes the sign. And we can show that directly. J cross I, remember j is the y direction, I is the x direction, so your thumb is pointing into the board, which is minus k direction. Okay? So this vector, j cross I, is minus k, and this one is plus k. So I can add these 2 terms together in front of a k vector. Okay, so let me write that. And if you'll forgive me, I'm going to erase the 2 vectors so I can write it up here. My answer has a term that looks like axby minus aybx all times k. So that is combining two of the terms. Okay, and now I can combine two other terms. I have a k cross I term. Remember that k cross I is j. Let's just double check that. K is in the out of the board direction. I is over there, so k cross I gives me the y direction. Okay, so this is the j vector. K cross I is the j vector. So I'm going to get a term that looks like az bx times the j vector. But I've also got an I cross k. And I cross k must be minus j, right? Because it's reversing the order of the vectors. Let's double check it. I this way, cross k. Okay, k is out, so I'm in the minus j direction with my right hand. Okay, so this will be minus axbz. Okay, and the last two terms are similar. J cross k, which is I. J cross k is I. J cross k is I. And k cross j, which is going to be minus I. K cross j is minus I. So that term will be ay bz minus az by times I. So that's how you do the cross product. It looks very complicated. It is a little bit, it's certainly more complicated than the dot product, but it's straightforward if you just, and it's good practice for your right-hand rule. The last thing I'm going to tell you is how to remember. You all now can easily remember that I cross j and j cross k and k cross I are either plus or minus the third one. Okay, whichever two you pick, the other one is plus or minus the third one. And let me give you a quick mnemonic for remembering whether it's the plus or the minus. Just write ijk, ijk. Okay, I went in the forward direction, ijk, ijk. If you go forward with any two adjacent pairs, it's plus. So I cross j is plus k. J cross k is plus I. K cross I is plus j. Okay? But if I do, for example, I go backwards, k cross j, then it's minus I. If I go backwards in this trio, I cross k is backwards, so it's minus j. Does that help? Okay, so now you know how to do cross products. You know how to do dot products. You know what a vector is. You know how to add vectors, subtract vectors, and multiply them by a scalar. What more is there to learn about vectors? Well, lots actually, but for Physics 1, this is what we'll need. So now you're experts in vectors and we can go forward and learn the physical laws that use these vectors.